Hi there, welcome to Just Another Dev, and today we are going to discuss about the stack data structure. So stack is basically a linear data structure. It follows the principle of FIFO, which basically means last in and first out, and the elements in the stack can be inserted or removed at only one end, right? So let's see what do we mean by a stack and what all these things mean over here, right? So if you see this thing, this is basically a stack, and if you observe this, you can assume that it looks like a pile of books, right? So assume all these things are nothing but books, and you have them arranged one after the other. I mean, basically one on top of the other, right? So if you see the last book over here, right? So even though it was added in the end, it will always go out in the first time, right? So, or whatever you are going to add next, let's say I add one more over here, then even though I added in the end, but if I want to remove this, this will go in the first time, right? I will have to remove the top one first. So that's why whatever comes in the last will go out in the first time. Yeah, so that's why last in, first out. Whatever comes to the last will go first. Okay, so I hope this is clear. What is LIFO? Again, it's a linear data structure. Linear data structure basically means it stores the data sequentially. As you can see here, we are storing all these things in a sequence. And this is also clear, right? So elements can be inserted and removed at only one end. So here we are only accessing the top, right? We don't have access to the other books or other elements over here, right? Only when I remove this, then only be able to access this one. When I remove this, then I will be able to access this one, right? So that's what basically a stack is. Let's look at the use cases for stack. So stack, as I said, is very common data structure. It is widely used in many applications. So one of the very common example is basically recursion. So whenever you are performing any recursive operations, a stack will be created and all your functions will be, whatever function we are doing a recursion on will be kept in this stack and then it will be taken out one by one. The recursion heavily relies on stack. The other example is undo and redo. So the undo and redo operations that we do on a daily basis in our IDEs and all, they also use stack internally. And the third one is function calls. So whenever we are calling some functions, let's say we have a function A, inside it we are calling function B, then we are calling function C and all. So all these things will be maintained on a stack. So once C is done, it will be moved out, then B will be moved out, and then finally A will be moved out. So that's how function calls also use stack internally. Okay, so let's see how we can implement stack. Okay, so let's create a stack.js file, and here we are going to implement our stack, and we are going to use linked list to implement our stack. If you are not aware of the linked list, you can watch my previous videos where I have explained what is a linked list, and you can come back to this video to see how we are going to implement a stack using linked list. Now, why linked list? Because as you saw before that we have to do a lot of pop and push, basically add and remove operations at one end in a stack, right? So linked list becomes a very good choice when we want to do a add and remove operation in constant time, right? Because linked list can provide this in constant time. So let's see how we can also do it. So I'll just create a constructor function over here, function stack. This dot stack equals to new linked list. I'll just do one thing. I'll import it. Linked list slash linked list. Okay. Okay. So now that we have our linked list, this is basically going to initialize our stack. Okay. Now what all operations do we need on our stack? So we should be able to figure out if the stack is empty or not. We can call it is empty. We need to see what is present at the top or find element at top or basically which is called peak. We should be able to push something to that stack. We'll just call it push and then remove something from the stack or basically pop. So these are the functions, main functions that we would need to implement in our stack. So let's see how we can do that. Okay, so let's create a isEmpty function. Sorry, not function dot stack dot prototype is empty. What we can do here is if our linked list has size 0, then we are going to say it is empty, right? So here we are basically doing a Boolean check. If the size is 0, we are going to say it is empty. Otherwise, we are going to say, it is basically going to return true or false. If the stack size is 0, it is going to return true. If it is greater than 0, then it is going to return false. So basically gives us the value for is empty. Okay. The next thing is, uh, let's say push. Okay. So we are going to push some value over here. And if the stack, uh, okay, let's see how we are going to push it, right? So if you remember, we push and pop at the same end, right? And in our linked list, we can access the first index in constant time, right? Okay, because first index is basically our head, right? So we can always access it. So what we are going to do, we are going to add and remove at the very beginning. So for example, if we say, okay, push 1, then our linked list will become like this, 1. If we say push 2, since we are pushing at the first index only, we are adding and removing from the first index only, it will become 2 and 1. If we have something like push 3, then it will become like this, 3, then 2, then 1. Okay. So here what we have to do, we have to simply this dot stack dot add at index 0 and then the value that we have here. Okay. So that's how we are going to push an element in the stack. Basically what we are doing, we are creating an element at index 0 in the linked list. Okay. Let's see how the pop will work. So imagine the state of our stack is this. Okay, if I say pop, so what we are going to do, since we are adding at index 0, we have to remove it from there only because stack only allows to add and remove element at only one particular end. Okay, so this will remove this 3 and we will be left with 2 followed by 1. Similarly, if we call this again, then we'll only have this 1 over here. So let's try to implement pop. What we are going to do, we are going to check if we actually have something in the stack. If it is not empty, then only we are going to return something. Okay, so if let's do this. If this is empty, we are going to return null. Otherwise, what we are going to do, we are going to say this dot stack dot delete at index 0. Okay, we are going to delete this thing, and we have to remove. We have to basically send this value back as well. So what we are going to do, we are going to return this node value. Okay, so what we did, if it is basically empty, we return null. Otherwise, if it is not empty, we are deleting whatever is present at index 0, and then we are going to return that node value. Okay, So this is what we are going to do. Okay, now let's look at the peak function. So peak is basically going to give us the value which is present at the top, right? Here again, what we are going to do, we are going to say, or we are going to basically check if it is empty or not. Otherwise, we are not going to delete, rather we are going to get the value at index. So there is a function called get node at index 0, and then we are going to return this value. Okay, so that's how we are going to uh, implement all these functions. So let's see how we can test these. Let me just save this. Let's create a test file. Test stack.js, or let me, yeah, that's fine for now. What we are going to do, we are going to get this stack. Okay, sorry, I think I did not import it. So let's export dot stack equals to stack. Now here we can import it. Okay, so it is automatically imported. Now what I'm going to do, I'm going to say stack.push. Let's push 1, then we are going to push 2, then we are going to push 3. Also, let's do a peek as well. What is basically present whenever we are pushing it. Okay, and let me just try to run it. Node test stack.js. Okay, that seems to be something wrong. What is happening over here? This dot is empty, return null. Otherwise, what is this dot empty going to give us? Okay, let's do a console.log. This dot stack. Let's just print the stack. What happens after push? Okay, it seems to be fine. We are pushing things in this thing. 1, 2, and then finally it is showing 3. Why this peak is not giving us correct thing? Oh, sorry. We have to invoke it. Okay, I think I'm not using it anywhere else. This should be fine. Okay, let me remove this as well. We don't want to print it. Okay, let's go back and see. Cool. So when we inserted 1, we are getting 1. When we inserted 2, we are getting 2. When we inserted 3, we are getting the top element as 3. Now let's do a stack dot pop and then see, or let's just see what gets popped when we are doing it. So 1, 2, and 3. 3 was inserted in the end, so 3 should be popped. Okay. So as you can see, we have popped 3. And if I do a stack dot peak now, then it should basically return me 2 because we have already removed 3. Okay, so 1, 2, 3, we added all these, and then stack.pop removed 3, and stack.peak is basically giving us this 2. So our implementation is working fine. So I'll just show it one more time. We are basically whenever we are creating a stack, we are basically initializing it with a linked list. And since we have to uh, basically add or remove element in a stack at only one end, we chose to add and remove from index 0 because in linked list, index 0 is basically always available. You don't have to do any iteration or anything. So it is a constant time operation. So that's why we are using index 0 over here. Same thing we are doing for pop, add at index 0, delete at index 0, and peek is basically going to get you the element at index 0. So this is what we are doing. Also, we have a check for the empty, if the stack is empty or not. So if the stack is empty, we are going to return null. Otherwise, we are going to proceed. So this is how basically we can implement a stack. So yeah, that's all about stack, how we have implemented it. Let's look at the time complexity of this. So let's talk about the time complexity of our stack that we have implemented. So basically there are three operations, which is basically our push, pop, and peek. And as we saw that we are using a linked list for all these operations, right? So this is basically our head, and we are always adding at this position, right? And since head is always available to us, right? So this is basically adding anything from at this point or removing anything at this point is always going to be a constant time operation, right? Because we are already having this head reference and we are adding it at index 0, right? All the three operations, push, pop, and peek, are happening at this particular index, right? So in all the three cases, the time complexity comes out to be O of 1. So you can push in constant time, you can pop in constant time, you can peak in constant time as well. Yep. So that's about the time complexity. The space complexity of stack is basically O of 1 because we don't need any additional space for all these operations. That's why the space complexity comes out to be constant time. So this is all about time complexity and space complexity of stack. Thanks for watching and stay tuned for the next video.